capacitors. Suppose we have two conductors and we put charges plus Q and minus Q on the other on the other well, on both sides, should we say. Since our potential is constant over a conductor, we can speak unambiguously of the potential difference between them as such. Now, we don't know how the charge distributes itself over two conductors, and calculating a field would be too difficult if they had complicated shapes, but we do know electric field is proportional to our charge. For the electric field given by Coulomb's law, we have this. So if you double our charge, you double the electric field, because doubling the charge does double the these are both charges, but yeah, doubles our charge, does double rho everywhere. If it doesn't shift charge around, since the electric field is proportional to Q, so also it is potential. Now the constant is proportional to our charge over our potential, and it is measured in farads. Now here's an example of a parallel plate capacitor, where A is the area and D is the distance between them. Now we find the capacitance of a parallel plate capacitor consisting of two metal plates of area A separated by D. Now the answer, if we put a plus charge plus Q on the top and a negative charge on the bottom, they will spread out uniformly over the surfaces, provided A is large and D is small. The surface charge density is then given here on the top plate, and so the field is given here. The potential difference between the plates is given as such. So our capacitance is then given by this. Now an example: two concentric spherical metal shells with radii A and B. Now we place a plus charge on the inner surface and a negative charge on the outer one. The field between the sphere is this, so the potential difference between them is given by here, as we've been through before, and our V, or potential, is proportional to our charge. The capacitance is given by this. The change up a capacitor to charge up a capacitor, you remove electrons from the positive plate and put them on the negative plate. Doing so, you fight against the electric field. So how much work does it take to charge a capacitor to find a final amount Q? Now suppose at some intermediate stage in the process, the charge on a positive plate is Q, so the potential difference is Q over C. The work you must do to transport the next piece of charge, delta Q, is here, delta W. So the total work necessary to go from Q equals 0 to Q equals Q is given by this here. Now since Q equals our charge equals our capacitance multiplied by the potential, so our work becomes this. V is the final potential of the capacitor. Now please do like and subscribe, there's lots more to come. I'm thinking of doing some game programming, C# programming in Unity and things like that to build games soon, as well as some Python kind of scripting and some other things, so please do like and subscribe.